Good afternoon. Today we are going to discuss the cosmic microwave background radiation. The discovery of the cosmic microwave background radiation has a very remarkable history. The history dates back quite early in the 20th century, well, the middle of the 20th century, and Lemaitre, Chandrasekhar, they all address the question of how the elements, the different elements were produced, synthesized, and to make these elements you require nuclear reactions, and nuclear reactions require high temperatures, high energy, because you have to bring the nuclei close together for fusion to occur. You have to overcome the Coulomb repulsion, so you require high energies. And it was realized that so you need some hot dense medium, and the nuclear abundances of the light elements in particular were found to be nearly the same throughout the universe, more or less the same. So you could, there were two possible sources by which you could synthesize elements essentially. One was inside stars, where you have the fusion process taking place. It's very hot, so you can synthesize elements inside the star. We have stars, we have already discussed this to some extent. And the other possibility is, suppose the universe is filled, suppose the universe had a very hot early stage. As the universe expands, the density of the universe falls. And if the universe is filled with a radiation component, then the density of matter, okay, the density of matter we have seen is proportional to a to the power minus 3, and for radiation it is proportional to a to the power minus 4. We have worked these out. Now, black body radiation, we know the energy is proportional to T to the power 4. So if I can characterize this, think of this as black body radiation, then the temperature of this radiation essentially falls as A, and when the universe was much smaller, the temperature then would have been much higher. Okay. So if you allow for the possibility, if you consider the possibility that the universe is filled with the radiation, then this radiation could have had a high temperature in the past, and the matter density would also have been very high, and you would have had ideal situation for synthesizing elements. So the early universe, it was realized, was also a possible place where you could synthesize elements. And the this entire thing was considered in detail by Gamow and collaborators. So George Gamow, famous Russian physicist, in 1938, okay, there was another collaborator of Gamow called Alpher, and they worked in around 1938, 1940s, early, okay, so 30s and maybe in the 40s also. They considered how these elements could be synthesized in a scenario where the universe had a hot phase in the past. So there was a radiation component which was hot in the past when the universe was much smaller. So for you need temperatures such that kT, for nuclear reactions you need temperatures so that kT is of the order of 1 MeV or higher. At these temperatures you can have, at these orders, temperatures of these orders, where K is the Boltzmann constant, okay, and T, so kT is of the dimension of energy, okay, this should be of the order of 1 mega electron volt. At these temperatures you can have nuclear reactions. So this was what they had considered. So they considered the production of light elements in such nuclear reactions. These nuclear reactions are taking place in an expanding universe, so it is not really in equilibrium, the universe is expanding. As the universe expands, the temperature falls, the densities fall. So there is a time range over which the nuclear reactions can really take place. It is a dynamical process. So they considered this production of light elements, and they predicted that if the light elements were light elements, I mean helium, lithium, deuterium, such elements, if they were produced by this mechanism, then there should be a radiation component also. The universe was hot, so there should be a radiation component, and that radiation component should at present have a temperature of the order of 10 Kelvin or less, of the order of that order, so maybe 5, 10, somewhere over there. Okay, so they predicted that if the universe had a hot phase where matter and radiation interacted closely and nuclear fusion could occur, then at present, when the universe has expanded considerably, the radiation should still be around, its temperature would have fallen and like this, and its temperature would be somewhere of the order of 10, maybe less, 5, okay, somewhere over there. All of this was before World War II, and during World War II people's attention was diverted elsewhere, so this was really forgotten for some time. And then in the early 60s, mid 60s, this whole idea was again revived. Zeldovich in Russia and a group in Princeton led by Decay, they again considered these ideas, and they predicted that there should be such a radiation, but the radiation was not observed at that time. So there was an ongoing effort at Princeton University, Rowley and Wilkinson, they were conducting an effort to carry out observations and see if there was really such a radiation filling the universe. So a radiation, a black body radiation whose temperature is of the order of few Kelvin, less than 10 Kelvin, of the order of a few Kelvin. So these experiments, this experimental effort was going on at Princeton University, and it was being carried out by Rowley and Wilkinson. Now at the same time, there were these two radio astronomers whose picture is shown over here, Arno Penzias and Robert Wilson. They were working at the Bell Laboratories, telecommunication company. So they were radio astronomers who were employed by the Bell Laboratories, a telecommunication company, and the Bell Laboratories had a radiometer which is shown over here, a very fine instrument, and these radio astronomers, they were working for Bell Laboratory, and what they were investigating was possible sources of noise for telecommunication, satellite communication. Satellite communication was just on the verge at that time. So they were investigating possible sources of noise for radio communication, and they had this radiometer. The radiometer incidentally was designed by Decay. It's a design. Who was the leader of the group at Princeton? which was carrying out experiments already to detect this radiation. So, this is a radiometer, decay radiometer, which had been designed by decay. So, they were investigating the noise for radio communication, and they were carrying out observations at around 7.5 centimeters. Which is which you would conventionally call the microwave part of the spectrum. And they found very interestingly that there was an excess noise. What do you mean by excess noise? So, you could predict the level of noise which your instrument should produce if everything is fine, and they were quite sure about what their instrument should produce. And if there was some excess from the sun could be emitting radio waves, it emits optical, so it could be emitting radio also, then that would have some 24-hour periodicity. When the sun was overhead, you would have some value. When it was away from the field of view of your radiometer, it would go down. There would be some modulation. If it was some other astronomical source in the sky, again the earth rotates, so there would be some modulation in the signal. But they found that there was some signal, an excess signal, some excess reading that they were getting, and which had no directional dependence. It was uniform from all directions, and this was referred to as excess noise. Excess noise. Okay, so the term that they used was excess. And they presented this. So one of them, gave a talk on this, and this talk was attended by a radio astronomer who again was in contact with this group at Princeton. So he visited Princeton, or he communicated the fact that they had found an excess noise, and the people at Princeton then discussed this with the people at Bell Laboratories, and they realized that the people at Bell Laboratories had discovered this cosmic remnant. If the universe had a hot phase, there would be a remnant still lying around, and these radio astronomers had actually discovered that. So what they discovered was actually an excess noise, and if you look at the paper, there are two papers which occur subsequently in the Astrophysical Journal. So there is one paper which is called Excess Noise at Some Frequency, which is a very short paper which just reports that there is excess noise, doesn't really go into the interpretation. And so this paper is by Penzias and Wilson. There is a subsequent paper, there is another paper in exactly the same issue, they are back to back, by Decay and their collaborators, where they interpret this excess noise in terms of a cosmological radiation. So they interpret this as a radiation that fills the entire universe, just like we have discussed the galaxies, matter filling the whole universe. They interpret this in terms of a radiation that fills the whole universe. This is a black body radiation whose temperature falls as a to the power -1 as the universe expands. As it expands, the temperature, the radiation cools, and they interpret this reading as a detection of that black body radiation. Now, we all know that a black body radiation, what is black body radiation? Let us just spend a little time in discussing this, right, to make sure we understand what we are talking about. So one way you can think of black body radiation is as follows. You have a cavity, so this is a cavity made of some material that can emit and absorb light of all frequency or wavelength with equal efficiency. It has no characteristic wavelength of frequency. So, this is a cavity which is enclosed in some material which is equally efficient in absorbing and emitting light of all wavelengths or frequencies. Okay. And this is maintained at some temperature T. Now, this cavity, this material, the walls of the cavity are going to emit photons, and the photons are going to be emitted and absorbed, reabsorbed, re-emitted and reabsorbed, and finally the photons inside this are going to be in equilibrium with the walls. So, these photons that are in equilibrium with the walls of the cavity can also be characterized with the same temperature T. Right, that is the zeroth law of thermodynamics. If two things are in equilibrium, they have the same temperature. So, these photons are in equilibrium with the wall outside. So, we can characterize the properties of these photons by a temperature T. Okay. And this is what we mean by black body radiation. The spectrum of this radiation, which we shall discuss in more detail later, is uniquely defined in term by the temperature, determined by the temperature. Once you know the temperature of this radiation, once you know the temperature of the wall, the spectrum of this, the spectral energy density, I nu that we have discussed, specific intensity, is uniquely determined by the temperature. Once you know the temperature, I nu inside is fixed. Okay, you do not have to tell anything more. The temperature inside is the spectrum inside, the spectral energy density is uniquely fixed by the value of the temperature. Okay. So, essential for black body radiation is that the radiation should be in thermal equilibrium with the matter through successive collisions. Once this occurs, the spectrum and every other property of the radiation is uniquely determined by the temperature, value of the temperature, nothing else. Okay. So, this is what we mean by black body radiation, and this remnant radiation was supposed to be a black body with a temperature somewhere less than 10 Kelvin, maybe 5, 3, 4, somewhere over there. Okay. And these, what had been observed was an excess at 7.5 centimeters. At one wavelength they had found some signal, some excess radiation. Okay. Now, there are then certain questions. How do you know this is a black body spectrum? You do not know, right? You do not know that it is a black body spectrum. So, you have to first measure it at other wavelengths also. You have to measure it from different directions in the sky. Once you, because if it is cosmological in origin, then sitting over here it should appear to be isotropic. Okay. And it should also have a black body radiation. So, all of these things were open questions at that time. Okay. Let me now show you, before this observation was reported, what was the status of different background radiation. So, this is a graph taken from Peebles, a book by Peebles. Peebles was one of the persons involved in this, closely involved in this whole thing. So, this is a graph taken from Peebles' book. This graph, it shows you at different frequencies the background radiation that had been measured, or upper limits. So, the background radiation could not be more than the value indicated here, or there were measurements, okay, over a whole range of frequencies. And at the frequency of our interest, there was an upper limit where the CMBR was discovered, where you expect the black body radiation at a few Kelvin, the energy density from that to peak. there was an upper limit which has been shown over here. Okay. And this was, these were the two people who made the observation, and what they detected was the radiation that they detected. The intensity of the radiation is shown over here, and the observation was at around 7.5 centimeters. So this is the point that they got. Okay, so they had one observation of some signal coming from outside the earth, and which had no source, definite source associated with it. Okay. Now it requires many other observations to establish that it is a black body. Okay. A point alone does not tell you that it is a black body. Black body has a unique spectrum. So if you could measure other points at other frequencies or other wavelengths, and if they lie on the spectrum predicted by a black body curve, then you would know that what you are saying is this whole thing about it being cosmological in origin, etc., is correct. Okay. Now this is the black body spectrum that you expect at, it's a black body spectrum at 3 Kelvin. Okay. So the measurement made by Penzias and Wilson could be interpreted as being a part of a point on a black body spectrum with temperature 3 Kelvin. Okay. So if you interpret this point as lying on a black body spectrum, the temperature that you get is 3 Kelvin. So this is the graph corresponding to that. Okay, it peaks. So this was not the peak. It peaks at millimeters and the micrometers. Okay. So 1/10 of a millimeter and a millimeter. This is in centimeters. So this is 1/10 of a, somewhere around millimeter or a little less than that it peaks. Fraction of a millimeter it peaks. So if indeed the universe is filled with such a radiation, then you can detect it, you cannot detect it at all wavelengths. There are other radiations there at other wavelengths, at different other wavelengths which dominate over this. Okay. So if you look at very large wavelengths, so this is 10 centimeter, close to where the detection had been made, but if you go to 1 meter radio waves, this is okay, 100 centimeters is 1 meter. If you go over here or even larger wavelengths, then the contribution from radio waves, radio galaxies, okay, the contribution from external radio galaxies and the synchrotron radiation in our galaxy, they dominate over this cosmic microwave background radiation. Okay. And it has a slope, the slope is given over here, lambda to the power of 2.4. So these are other radio sources, these are sources, radio sources, it is not cosmic. Okay, you can identify sources corresponding to this. And the contribution from these sources, so one of these sources is our galaxy. How do you know it is our galaxy and not cosmological? I am getting a radio emission. How would I know that it is our galaxy and not cosmological in origin? It will not be isotropic. Our galaxy is a disk. When the disk is overhead, when the plane of the disk is overhead, when I look along the plane of the disk, the radiation would be more. When I look, so this is a disk of the galaxy. If the radiation originates in our galaxy, if I look inside the disk, we are located somewhere here. If I look inside the disk in these directions, I will get more. If I look perpendicular to the disk, I will get less. So that tells me that this is galactic in origin. Okay. Then there are extragalactic radio sources. These are points from where the radiation originates. You can make out that it is there from a particular direction, not there elsewhere. Okay. So these sources dominate at this part of the wavelength, and if you go to shorter wavelengths, then the radiation is dominated by starlight and dust, right? You are heading towards infrared and optical. So there is dust in our own galaxy. The dust absorbs the optical radiation, we know this, right in the beginning we discussed this, and it re-emits it, the dust, the temperature of the dust is such that it re-emits the radiation in infrared and in millimeter waves. Okay. So there is dust, and there is also the combined starlight from all these stars in our galaxy, okay, which dominates at smaller wavelengths, higher frequencies. So there is a window over here. We are very fortunate, there is a window over here, and if you don't know about this, but by chance if you look in this window, the dominant radiation is that of this black body radiation that fills our universe. So if our universe is filled with the black body radiation with temperature 3 Kelvin or somewhere over there, it would be the dominant component in this wavelength range. And Penzias and Wilson had made an observation in this range at 7.5 centimeters, and they had found a point, and which if lies on a black body spectrum of 3 Kelvin. Subsequently, there were, so in the mid 60s there were several other observations, and in 90s, early 90s, 1992 I think, there was a satellite experiment called COBE. Cosmic Background Explorer. COBE had several, okay, before I come to COBE, let me just discuss this. So there were several experiments at different wavelengths. So this is the wavelength, and the Earth's atmosphere is transparent for radio waves. It is also transparent for microwaves, but it is not transparent at millimeter waves. Okay. There are water vapor, there is water vapor in the Earth's atmosphere, and the water vapor has rotational and vibrational levels, particularly rotational levels, which absorb the millimeter wave radiation. So the vibrational frequency matches with those of these radiation, so it absorbs it, it does not pass through. Okay. So it is, you have to, if you want to do observations at these wavelengths, millimeter and sub-millimeter, less than a millimeter, you have to send your instrument above the Earth's atmosphere. Okay. So on the Earth you can observe at centimeter wavelengths, and you can observe at larger wavelengths. So these were the observations that were carried out from the Earth mainly using decay radiometers, these observations, and they all were consistent with the black body radiation. Okay. And then there was this satellite, there were balloon borne experiments, and there was this satellite called COBE. Now COBE had several instruments, which I shall, some of them I shall talk about later, but one of the instruments was called FIRAS, far infrared spectrometer, and this solid curve over here is are the readings from COBE observations. So this shows you just the COBE observations. They probe the peak of the black body spectrum where you expect the peak radiation, and these were the COBE results. They show that this radiation that we see from outside the Earth is a very good black body with temperature, the best estimate of this temperature is around 2.736 plus minus 0.017 Kelvin, and these are based on Kobe and balloon borne experiments. Okay. So, Kobe showed, the Firas experiment on Kobe, it showed that the spectrum of this radiation is very, it's a very good black body with temperature 2.736 plus minus Kelvin, and the 1 sigma errors on this spectrum have been magnified 20 times, otherwise you would not be able to see them on this graph. So, this shows you the Firas observations of this background radiation. It is the best black body spectrum that has ever been measured. Okay. So, a black body spectrum has not been measured with this accuracy elsewhere before this on Earth. Okay. So, it establishes that this radiation that is coming, which was detected by Penzias and Wilson originally, is indeed a black body spectrum. Incidentally, Penzias and Wilson both received the Nobel Prize for this discovery, and John Mather, who was the leader of this instrument, on the team that made this instrument, planned and designed and made this instrument, he also received the Nobel Prize last year. Okay, so these are very important discoveries in the evolution of cosmology. The discovery of the cosmic microwave background radiation is the most important single most important discovery after Hubble's discovery that the galaxies are all moving away from us. Okay. So, what are the two key features of this discovery? One key feature I have already told you, that it is a very good black body. It is very well described by a black body spectrum with temperature 2.736 Kelvin. Okay. Now, the fact that, let me dwell upon a little bit upon this. The fact that it is a black body spectrum, it has a black body spectrum, a thermal black body spectrum, is very important. To produce a black body spectrum, I have already mentioned that you require radiation. You require radiation to be in equilibrium with matter to produce black body spectrum. Right. This is in this picture I have explained to you how what we mean by black body radiation. It's a thermal radiation, another term that. So, you require radiation to be in thermal equilibrium with matter for radiation to have this kind of a black body spectrum. Okay. Now, how do we interpret? So, what we see is that we sit over here and we see this radiation coming towards us. It is highly isotropic, so it is more or less the same in all directions, and it has a thermal spectrum, a black body spectrum. The question is, how do we interpret this? For it to have acquired this black body spectrum, it should have been in thermal equilibrium with matter. Right. Now, we know that the universe is transparent at these wavelengths all the way to redshifts of 1, order unity. So, I am an observer over here, Suppose the photon is emitted from a redshift of order unity, and we know from observations that the universe is transparent, roughly transparent to such photons. There may be some amount of absorption. How do we know this? We know this because at centimeter, millimeter wavelengths we can observe galaxies up to redshift of 1, 2, 3. Okay. So, the fact that you can observe galaxies means that the photons can propagate to us from those redshifts, otherwise you would not be able to observe galaxies at those redshifts. Okay. So, if the photons can propagate to us from those redshifts, the universe must be transparent. So, we know that the universe is transparent out to redshifts of order unity 1, 2, 3 till those redshifts. Okay. So, this radiation that is coming to us could not have originated somewhere in between. So, the radiation that is coming to us from all directions could not have been in thermal equilibrium, could not have arrived at thermal equilibrium somewhere before a redshift of 1, 2 or 3, somewhere over there, right. So, this radiation that is arriving to us has propagated freely for nearly the Hubble radius. The Hubble radius, we have defined the Hubble radius. What do we mean by the Hubble radius? If a photon starts propagating at the Big Bang, the distance it can cover by now is the Hubble radius, right. So, that is the furthest distance I can see. Let me redraw this picture. So, I am an observer over here. The furthest I can see is this, that is the Hubble radius, and there is evidence that the universe is transparent for a considerable fraction of the Hubble radius. We reach a considerable fraction of the Hubble radius by a redshift of 1. Remember, we have calculated this in a omega matter equal to 1 model. We are at half the Hubble radius by a redshift of half the horizon, the furthest distance that you can see, by a redshift of 3. Okay. So, the universe is transparent. So, the photon has, there is no scope that the photon could have come to thermal equilibrium over here. So, there is no scope. Okay. So, this leads us to the picture where the universe, so you cannot postulate the presence of sources over here distributed inside this, which could have produced this radiation. Okay. So, the only way you can visualize this radiation is that this is some thermal radiation that fills the entire universe. Okay. It is cosmological in origin, you cannot associate it with some source, and this radiation was in thermal equilibrium with the matter in the universe at some epoch over here, at some redshift over here, when the universe was much smaller, the radiation was much hotter. Okay, as you go into the past, the radiation gets hotter. So, the only way you can interpret this is that this radiation was in equilibrium with matter at some very high redshift of the order of 1000, we know now. When the temperature of this radiation was, the scale factor at a redshift of 1000 was 10 to the power minus 3. The temperature is proportional to A inverse. So, at that epoch the temperature of the radiation was 3000 Kelvin, it was much hotter, and the universe was also much denser. Okay. So, it was in equilibrium at some early time in the past, then it went out of equilibrium, and this radiation now fills is a radiation which is cosmological in origin. It fills the whole universe. We are embedded in this radiation. You cannot associate it with sources inside over here, because we know the universe is transparent, the radiation cannot come to equilibrium with such sources. Okay. So, this is the way we visualize this radiation. It is a radiation that fills the whole universe. It is a cosmological radiation. Now, the radiation is found to be isotropic to a high degree of accuracy. What do we mean by isotropic? Let me first explain this. So, I take a radiometer, I am sitting here, I take a radiometer and point it in different directions. So, I can measure the temperature of the radiation as a function of direction. N is a unit vector in the sky pointing up different directions. And it is found that this is isotropic to a high level of accuracy. Okay. That is, the temperature of the black body radiation, if I measure it in different directions, is more or less a constant to a high level of accuracy. There are deviations, small deviations from this isotropy, which are very important. So, there is a 0.1% deviation in the temperature across the sky. So, the temperature changes by 0.1%, okay, and this is a dipole. So, this has a cos theta dependence. So, there is a delta T proportional to cos theta, where there is a, so this is a pattern like this, there is a preferred direction and there is a change in the temperature which is a function of cos theta. It is a dipole pattern. What I mean by this is that the temperature is in excess in one direction where theta is 0. It is, there is a temperature decrement in exactly the opposite direction. At 90 degrees there is no change in the temperature, it is exactly the mean value. Okay. So, there is a dipole observed. So, it has a there is a temperature fluctuation which has a cos theta dependence. It has a positive sign in one direction, a negative sign in the opposite direction, the temperature difference, and it is 0 along the perpendicular direction. And this can be interpreted in terms of our own motion. So, we are moving with respect, so this cosmic microwave background radiation is homogeneous and isotropic, it is cosmological, okay, but if you move with respect to it, then obviously it will no longer remain homogeneous and isotropic. In some direction there will be a blue shift, some direction there will be an excess red shift, and this is what we see as a 0.1% anisotropy, a dipole anisotropy of 0.1% in the temperature. Okay. In addition to this, we have, it has been observed that there is a fluctuation which is of the order of 1 part in 10 to the power minus 5, okay, or delta T is of the order of 10 to the power 5 into 3 Kelvin roughly, which is tens of microkelvin, tens of microkelvin, right, tens of 10 to the power minus microkelvin of this order. So, that there are small fluctuations in the temperature across the sky, and one can decompose these fluctuations into angular harmonics. So, you have the quadrupole and higher, this is the quadrupole and higher angular harmonics. So, the quadrupole is a fluctuation like this, where it has a positive sign here, negative value here in the sky. Okay. So, there are tiny fluctuations which are more rapid as a function of angle than a dipole, and these fluctuations are related to the formation of large scale structure in the universe. They probe the formation of large scale structures in the universe. So, I have shown you pictures of the galaxy distribution, for example, where you see that there are structures in the galaxy distribution, right, and there are clusters of galaxies also. So, all these structures in the matter, they formed, we believe that they formed by some process in this expanding homogeneous and isotropic expanding universe. And these fluctuations that you see in the cosmic microwave background radiation, these tiny fluctuations, are actually probes of this formation of large scale structure. And these fluctuations, the tiny fluctuations, were first discovered by this Kobe satellite. There was another instrument, the Darby instrument, So, the leader of that group, George Smoot, he received the Nobel Prize for this discovery also. Okay. So, both of these were extremely important discoveries. The fact that it is extremely isotropic was a very big discovery, but the fact that there are small anisotropies also was a very important discovery, which were both, and they received the Nobel Prize for that also. Now, the discovery, so we shall deal with the interpretation of these things as we go along. I have just told you what the main findings were and what their significance is. The discovery of the cosmic microwave background radiation, as I have told you, was the most important single discovery since the discovery made by Hubble that the universe is expanding. Okay. Let me explain how it revolutionized cosmology. Hubble's discovery had told us that the universe is expanding. There was no doubt about that. Okay. Fine, the universe is expanding. Now, at the time of the discovery of the cosmic microwave background radiation, there were two competing theories of cosmology. One was the evolutionary model. Okay. What do I mean by the evolutionary model? In these models, as the universe expands, the density of matter in the universe falls as a to the power minus 3. If I have a radiation which is cosmological, its density falls as a to the power minus 4, etc. We have been discussing this. Okay. There was a competing model called the steady state model. In the steady state model, the universe is expanding. Both of them have to be expanding because Hubble had discovered this. So, the universe is expanding. You cannot have a theory which does not agree with observations. So, both these models were expanding models, but in the steady state theory, the expansion was such, the whole theory was such that even though it expanded, everything in the universe remained the same. Okay, the density remained a constant, it did not expand, it did not change with the expansion. Okay, so both these models were expanding model, but the density here remains a constant. Now, you may be wondering, how is this possible? How does it happen that the universe expands but the density remains a constant, right? Now, just recollect, how did we arrive at these? We arrived at these from the conservation of energy, right? Now, if you modify those, if you have energy being produced by some means, or if you modify the laws of physics, then you can construct models where the universe has a steady state. It is a steady state, it expands, but there is matter created by some means which compensates for the expansion, and the universe remains in the same state on the average. We have already considered a situation where this possibility can be implemented. That is, if we have a cosmological constant. If you have a cosmological constant dominating the universe, it is like a steady state cosmological model. As the universe expands, the density does not change. The Hubble parameter is a constant, right. So, we have seen this. So it is so the steady state model was a model which was a competing model at the time before the discovery of the cosmic microwave background radiation, and you had these two models which were, and the question was which were there, and the question was which of them is correct. They are conceptually quite different. Okay. In the steady state model you could have an exponential expansion, and then you don't have a big bang. You don't have a big bang. The concept of a big bang is not there in a steady state model, right? That violates steady state. Right? There is no origin of time in a steady state model. So the steady state model people had called this the Big Bang model as a kind of derogatory remark. Okay. This is an evolutionary model, it's a Big Bang, you know, failure, Big Bang, it will end up with it's a failure model. So they had given this name, so this was the Big Bang model. Okay. The Big Bang, the term Big Bang was not coined by people working on this model. The term Big Bang was actually coined by people, the name given to these evolutionary models, the Big Bang model was actually coined by people working on the steady state theory. Okay. Now the cosmic microwave background radiation gave definite proof that the steady state model was not the correct model and the evolutionary model was the correct model. Let me explain to you how it indicates that the evolutionary model is the correct model and not the steady state. Let us go back to this picture. The universe around us is transparent to this radiation that you are seeing with the black body spectrum. Right. The universe around us is transparent to this radiation that you are seeing with the black body spectrum. Now if you believe in the steady state model, then the universe was always like this. So it expands, the density falls, but there is more matter created by some means or whatever, the laws of physics are different, and the universe is always transparent, not only here but elsewhere in the universe also. So if you have a universe like this, then you cannot get matter in thermal equilibrium with radiation because it is transparent, they don't interact much. Okay, so that is not possible. Now people, so you do not have a very natural explanation for the cosmic microwave background radiation in this steady state model because the universe is transparent. You cannot have radiation and matter in thermal equilibrium. Now people working on this steady state model, what they tried was as follows. They said that there are stars in our galaxy, in neighboring galaxies. So the stars produce enough energy. If you could convert this energy that is produced by the stars by some means into a thermal radiation at 2.73 Kelvin, then you might be able to explain this cosmic microwave background radiation. Okay, but how do you convert starlight? Starlight peaks at some optical visual, in the visual somewhere over there, infrared. Right? Stars don't produce radiation, stars are at much hotter objects. Right? The black body spectrum is quite different and each temperature has its own black body spectrum. So how do you produce this 2.73 Kelvin radiation from starlight? So they tried dust. So what they did was they put dust, the dust absorbs the starlight and re-emits it, and they tried to construct models where you could explain, they tried to explain this, but it really is quite contrived and it is now generally accepted that the steady state model is unable to explain the cosmic microwave background radiation. In the evolutionary model, what happens is that as the universe expands, as you go to the past of the universe, the radiation was hotter, the universe was denser, so sufficiently back in the past. So this is, I am tracking the radiation as I go back. Sufficiently back in the past, the radiation was hotter, the matter was denser, and they were in thermal equilibrium. So you have a very natural means of explaining this in this model. You have a very natural means of explaining the black body radiation. Okay. Now, as you go back in the past, the temperature of the radiation exceeds 1 mega electron volt, 1 MeV, and then before that the temperature of the radiation was sufficient to dissociate the nuclei. Okay, so there is a, as you go back in the past, there is an epoch when the temperature is sufficient to dissociate all atoms. Further back, the temperature is sufficient to dissociate all nuclei, so you don't have any bound nuclei. Okay, if you go further back, the temperature of the radiation is sufficient to even dissociate the quarks inside the protons and nuclei, the neutrons. Okay, so you have a whole thermodynamics now taking place. The temperature gets hotter and hotter as you go to the past, or if you work in the historical direction, I mean, if you follow the history, you start off with a very high temperature, and as it cools, different reactions, the different objects can be in equilibrium, and you have the formation of different kinds of things, and you can explain the light element abundances, etc. Okay, so this sets a temperature scale in the universe. As you go into the past, now you have a temperature scale. The redshift and temperature are related. Okay, so these are things which we shall take up as we go along in subsequent lectures. Let me stop here for today.